First, I would like to thank organizer for giving me this opportunity for present my work. So today I'm going to present the work which I had done 1 year back. So the title of my talk is Constraining the Dissipative Dark Matter from Global 21 centimeter Signal. Some part of it already covered by my previous speaker Halder, and I will just go deep in that. So okay, so we know that dark matter exists. There are a lot of evidences that tells about that dark matter exists. But for example, galaxy rotation curve and also the bullet cluster, and then so it basically tells about dark matter exists, but they don't tell about what kind of dark matter are there. Whether dark matter, cold dark matter, warm dark matter, and other so kind of candidates. So because of that, and also there are many problems with the lambda CDM model of cosmology. For example, if we take only cold dark matter scenario, so we have a lot of problems. For example, dark energy and small scale problem, focus problem, so on. So in order to reduce those problems, many different models of dark matter have been proposed. So in the standard description of the cosmology, dark matter is assumed to be perfect fluid. There is no dissipation, don't interact with the standard model much. And but what happens? What happens when we assume that dark matter is a not ideal fluid? It is basically dissipating fluid. It have a viscosity or some other dissipative property. So basically, it modifies the standard evolution of the universe, but it also on the same time provides a new consequences that basically we can see. So it has been argued that if dark matter have a viscosity, then you can explain the dark matter have viscosity, then you can explain the late time cosmic acceleration, and also if the in the very early of the universe, if cosmic fluid have a viscosity, then you can also explain the early time accelerated expansion like inflation. Also, it had been realized that if self-interacting dark matter have a viscous property, for example, self-interacting dark matter have been proposed to solve the small scale issues, but we have showed that if self-interacting dark matter have a viscosity, then it basically explain the late time cosmic acceleration without need of any cosmological constant. And also, it has been shown in some of the work that viscous dark matter can also solve the problem what the lambda CDM faces. Like there is a tension between Planck and the local measurement. So if you take the viscosity in the cosmic fluid, then you can explain that tension in the local measurement and global measurement. Okay. So motivated by this fact, we just talk about, we consider that dark matter have a viscosity. So we don't consider dark matter, so viscosity two types like shear and bulk viscosity, but shear viscosity is related with the anisotropy of the dark matter, and therefore we know that on the very large scale universe support the homogeneity and isotropy. Therefore, universe don't allow the anisotropic part on very large scale, although it's very limited, very small number. But since the bulk viscosity is very consistent with the homogeneity and isotropy of the universe, therefore we assume only bulk viscosity into the cosmic medium, and we assume that viscosity only depends on the density, dark matter density. Zeta naught is just a constant, and once we have a viscosity in cosmic fluid, then it basically dissipates and it produces the entropy. And so entropy in the homogeneous and isotropic background, the entropy production is given by this expression, where H is the Hubble expansion. And also, once we have entropy production, then it dissipates energy into the cosmic medium and heats the cosmic medium. For example, if dark matter have bulk viscosity, then it heats the dark matter. Here I have showed for different alpha values. Here you see that on the very large redshift, dark matter we have considered that basically the temperature of dark matter very small. It is also true because if dark matter have produced, let us say, thermal dark matter, then if you just assume the redshift evolution of the dark matter, it turns out to be very, very small, and therefore we safely assume dark matter temperature to be zero around decoupling. And once we have initial condition, then using the viscosity expression, we can just calculate what is dark matter temperature. And here you see that it turns out that if dark matter have a viscosity, then it increases its temperature. And the main thing is that the temperature is important in the late time of the cosmic evolution. Although it's important early, but here we are just discussing the late time. And we also mentioned that this viscosity, if you take that value, I have not mentioned, but zeta bar, that is basically related with zeta naught, is 10 power minus 14, and that will not change the Hubble expansion rate. So you are safe in that sense. So you can basically, the dark matter temperature increases on the low redshift. But if dark matter temperature increases, so it basically reduces the growth of density perturbation and structure will not form. So you don't allow much viscosity into the dark matter. So there is a constraint on dark matter temperature, basically velocity dispersion of dark matter. And if velocity dispersion is less than particular value, then dark matter is consistent with the universe, what we observe at current in the universe. But if temperature is very large, then dark matter behaves like a hot dark matter and a warm dark matter, and then structure will not form. Okay. So so we now we will discuss what kind of effect it will show on the cosmic evolution. Okay. So here we know that, so already 21 centimeter have been discussed. So I will not just discuss about that, but here I will discuss that 21 centimeter temperature is basically depends on the number of hydrogen atoms, spin temperature, and the CMB temperature, and also the Hubble expansion rate. So in order to effect the 21 centimeter signal, either so one can modify spin temperature, CMB temperature, or the Hubble expansion rate. And okay, so this is what edges measurement has been reported, and it has been argued that if you take only the standard model of cosmology, no viscosity, no other dissipative phenomena, you can have only temperature is only minus 209 millikelvin, but edges has observed dip on those particular redshift at z equal to 20 to 15, between that, and it peaks around z is equal to 15 to 50 to 17. And what is the explanation corresponding with that? So we will talk about the explanation from the dark matter perspective. Okay, so here we see that at that time, when at the cosmic dawn era, only dark matter is a candidate whose temperature is very small, baryon is very hot. So in order to solve the problem, in order to explain the anomaly, one need to decrease the spin temperature, that is typically gas temperature. So what it can be done by dark matter baryon interaction. Dark matter is very cold, as I told you, and baryon is very hot. So if there is some interaction, then baryon will transfer its energy to the dark matter, and therefore it can reduce the spin temperature. And also, if you increase the low energy photons, and so basically if you increase low energy photons in the CMB Rayleigh-Jeans limit, then you effectively increase the temperature in those particular Rayleigh-Jeans limit, and also explain the 21 centimeter signal. And there are some other proposals, for example, early dark energy and 21 centimeter exhaust, but I will not talk about that. Okay. So here this is the temperature evolution of the dark matter baryon. So here we consider that baryon interact with the viscous dark matter. So here this is the standard evolution, this is Hubble expansion rate, this is the Thomson scattering, and this is the energy transfer rate from the dark matter to, from the baryon matter to dark matter. This is given by this expression. Here you see that, so dark matter at baryon temperature is different. So this heat transfer rate basically depends on two terms. First is temperature difference term. It shows about if there is two fluid, then okay, if temperature of dark gas is large in temperature to dark matter, then it will transfer heat. And particularly if the mass of the dark matter is larger than 1 GeV, then this term becomes very important, and it will heat the dark matter and baryon term. You cannot solve the problem. Okay, that's why your temperature will be small. Here I have shown that for particular zeta value, the temperature, if you see this is the blue curve is corresponding with the no dark matter baryon interaction, and here you see that its viscosity is very small, then dark matter basically just give energy to the baryon. So baryon gives energy to dark matter. And but if the viscosity becomes very large, then after some time, even dark matter start heating, and therefore you cannot solve the edges. So, and here also you see the effect of the sigma. If you increase the sigma, then basically you decrease the baryon temperature and you may solve the problem. So, in order to solve the problem, you need to decrease the mass of the dark matter or viscosity. Either you need increase the dark matter baryon interaction. So, this is the typical dark matter brightness temperature as a function of redshift. Here I have not included any heating effect. That's why the curve will not looks like what we see. So, here you see that as you increase the viscosity, the 21 centimeter signal becomes very low, and you cannot explain the signal. Okay, this is the sigma versus m plot. Here you see that as you increase the viscosity, so you need to effectively increase the sigma in order to compensate that energy dissipation mechanism, and that basically you reduces the mass of the dark matter. If you increase mass larger than that, then basically the another term which I showed you, that will be effective, and it will heat the dark matter and baryon. So this basically restricts the dark matter mass up to 0.1 GeV, lower than 0.1 GeV, and but also if you take sigma maximum from different particle physics experiment, and you take m is particular this value, you can also constrain the viscosity parameter. And here we see that viscosity is very large. If you want to just see the heating effect with the viscosity is very large in compared with the structure formation limit. The structure formation limit is 10 power minus 8 approximately. And also the dark matter coldness criteria, which I told you, that also have put the tight constant on dark matter viscosity. It's 10 power minus 10. So here you see that dark matter basically viscosity should not be large, and here edges constraint doesn't constrain viscosity, and only the dark matter coldness criteria provide the tight constraint on viscosity. So here we have seen the different explanation of the edges signal. It is that if dark matter energy dissipation is in the form of standard model particles, for example photons, then it will increase the photons on the Rayleigh-Jeans limit, and therefore it can explain the edges. So we have considered two possibilities. First, when there is a small interaction between dark matter and the photons, and there is a second interaction, that is dark matter to go to dark radiation, and there is a coupling with the dark radiation. And so here you see that number density of the photon produced because of this mechanism. Here you see on the large scale, on the large frequency limit, this is CMB, and this is for the dark photon produced because of dark matter viscosity. It basically increase the number density on the low frequency, but doesn't affect the large frequency. Therefore, it can explain the edges on this energy range. And in order to address the edges anomaly, the number of the dark photon produced in that low energy is order of Rayleigh-Jeans limit of the photons. So, and this is the dark matter parameter, viscosity parameter, if you constrain that, and this summary. So the idea is to dark matter if viscosity, then it will increase the dark matter temperature, and if dark matter temperature is large, then it will affect the evolution of the density perturbation, and it creates problem in the structure formation. And also if dark matter coupled with the standard model particles, baryons, then it also heat them and also create the problem for 21 centimeters. And okay, so yeah, thank you.
Thank you, Arvind. We have any question? A lot of questions.
So again, as some talk from the morning session alluded to, is a null detection going to be an interesting constraint on this?
I think as I told you that viscosity from edges, even edges allow large viscosity. So edges doesn't affect on the viscosity parameter. Even this structure formation basically limits the viscosity of the dark matter.
There's a question from this side. Okay.
So probably you have said, but I missed, what is dark radiation and how it couples to dark matter?
Okay, so dark radiation is kind of photon kind of thing, but it have mass. So it's like not exactly, you can say like neutrino have very small mass. So it coupled with the dark matter, with the baryonic matter, the photons I will say, that is with kinetic mixing parameter. So somehow it connects with the kinetic mixing parameter. So there is a mixing parameter that tells about how much coupling is there. And there is a probability how one can calculate how many number of dark photon converted into the photon.
There is a question here.
How cold the cold dark matter is, because the viscosity is going to zero. So it is kind of a Bose-Einstein condensation or what? I mean, viscosity goes zero only in the Bose-BEC regime, right? So
yes. There is no dissipation.
yeah, so it's.
So if you say like, I would say that if dark matter in cosmological perspective, I will say, in the cosmological perspective, if by dark matter has any velocity dispersion, then definitely it will going to affect the density evolution equation and structure formation. So since we know that there is a structure, by that we can constrain what is the sigma, what is the corresponding growth of density perturbation, and that limits the dark matter temperature. And the basis you can say how cold dark matter is. Basically, what limit I have showed T by M, that is how cold you can be. And also this limit doesn't valid on the late time because there is a structure formation and there is some viral temperature and other temperature. I'm not talking about that. I'm talking about the linear regime, and this is the constant what people have got. That if you are increasing temperature larger than that, then basically the structure formation will be influenced after that, and you don't have a structure.
There is a question on that side.
Okay, so the dark matter to be viscous. So what kind of particle interaction or dissipation interaction?
Yeah, it's nice question.
It is a particle. So
Yeah.
what kind of interaction do we?
Okay. So we have discussed like how viscosity can come in the self-interacting dark matter. This is one example. So dark matter is like two body, two scattering, two going to two scattering. You can calculate using kinetic theory, using the fluid and corresponding the kinetic theory correspondence. You can have expression what is the viscosity related with the distribution function of the dark matter.
But can you go to the page 13?
13? Yeah.
It is self-interacting. I think there should be some constant already from other kind of from particle physics aspects. So the dark matter mass and cross section, there should be some constant.
Yeah. So actually, this sigma is dark matter baryon interaction, not dark matter self interaction.
Okay,
Yeah,
I understand. But in the context of dark matter mass, there should be some constant from self-interaction dark matter. So there should be some forecast problem and those things.
Yeah. So there are. Actually, what we have showed in our that paper, forecast problem or small scale problem basically suggests sigma by m. Why sigma is dark matter self interaction 0.1 centimeter square per gram. And that paper we have showed that with 0.1 centimeter square per gram you can explain the dark energy. So that value is same. You cannot, and also the velocity dependent on the galaxy velocity will be large.
Thanks.